to the fourth lecture of Intelligent Systems. And today I'm going to talk about adversarial search and advanced adversarial search. So up to now we always had problems that were represented as state spaces without some other agents interfering in the game. In the problem itself and in the environment. And now today we want to look into problems where we have agents, a multi-agent setting, an environment where someone else is trying to achieve other goals that you might want to achieve. And the best setting to do that, to test out and to learn, or a very good one at least, are games. So today is going to be more or less about games, but the techniques that we develop, they are applicable in many other domains as well. Still, we want to spend most of the time today with different kinds of games and looking at how we can develop algorithms now that take into account adversarial motives of some other agents. So in the sort of decision-making stack that we're working on, we have looked at the use of heuristics in the search, and we're now looking at opponents in search. And as I said, games are very useful in this environment for several reasons. The question is, in this multi-agent environment, what is the intention of another agent, and how do I have to deal with this agent? And in many of those environments, we have agents that collaborate. But in this competitive environments where the other agents want to achieve something else, and you want to achieve, the games are very good examples. And why are they good examples? First of all, they are quite nice. It's easy to talk about them. They're quite fun. You can play them yourselves. But I think the most important thing is that they are built for other people to use and for having very strict and clear rules. So we can define our problem in a very restricted way, and we can explain very well how these things work. So as we have usually games with the people, traditionally these games have very few agents. The rules are finite. They are in a space where we humans find it very challenging and sometimes, but also still something we can understand and link with. So that's why games have historically always been of big interest in AI. And I've talked about these historical moments that at least I can remember in the 90s, when the first chess computer was finally able to beat the world champion of chess, the match 1996, Kasparov against Deep Blue. It was at the time an IBM computer. And that was, at the time, it was really considered a miracle of technology. And it was very nice because it really got into the news, because this was something people could relate to. People could understand, wow, we now have a computer that can beat Kasparov in chess. And the same holds with, of course, developments 20 years later, that now we are capable of playing Go better than the best human players with an AI, with the AlphaGo. So, and for us, we use Schnapsen as an example because it has some very nice properties of a game. It is a relatively simple game. It is something where you can draw the problem still on the board. It is still something that is very exciting if you play it better. It has, in these two phases, it has very interesting properties in the different phases of the game. So we're going to take Schnapsen as one of the examples for how this game works. And of course, we will look at some simpler games to introduce the ideas in some simple way. For the search that we've seen so far, there is no adversary. So the solution is just some heuristic way of searching through the search space, the state space, to come from the board position I'm in to something I consider the goal, and nobody's sort of stopping me. So that works for solitary, that works for the Schnapsen light that I talked about, but it doesn't work when we have someone pulling the strings in the other direction. And still, I showed you yesterday the examples how difficult it can be and how big the search space can become, and how useful this can become in some application areas, such as planning or scheduling and so forth. Here now, the solution is not a path from a node to an end, but it must be a strategy, because I don't know what my opponent is going to do. So let's see how we can represent such a game in a state space, and then what it means to find the solution. Again, we are going to work with heuristics, and we might not always find directly the systematic way of considering the entire space of the game. So in chess, remember, we had these 24 by 24 and or 20, depending on the number of moves you can make per layer of choices, and this becomes far too big. So we need to sort of approximate the strategies and the goals and so forth, and this is going to be what we're looking into in the next couple of hours. So think of some different games that we know. So with chess, and in which environment they operate in. So we have, remember the agent environments that we wanted to, that you can classify your problem space in, and we have the question whether you have perfect information, imperfect information, and whether you have deterministic game, deterministic situations, or probabilistic, so an element of chance in it. And in that classification, we have in this space, we know everything about chess. So if you see the full board, you know the figures your opponent has, and the same holds for Go or other games like checkers. This is not the case for Schnapsen. So for Schnapsen, you know that we have imperfect information because we do not know where the cards are. Still, it is a deterministic game because we have the position, we have handed out the cards, and it will never change again. So it is clear that the pile of cards is here, and the cards in the hand will never change. There is no element of chance in it. So that's why these two sit under the header deterministic. So these are deterministic games. And we also have the non-deterministic games such as backgammon, where at each stage you have you throw a dice, and one of the different situations, new states can occur from this element of choice. And we're looking at those kind of games later. And then you have games that combine these two, such as poker, where you do not know your opponent's card, and there are new cards given that change the game in a probabilistic way. So you do not know upfront which kind of cards you might be handed in the next moves. So this is an interesting distinction we can make about the different kind of games. We can even go a step further. So the first phase of Schnapsen is indeed an imperfect information game, but after you've played 5 cards, you know in principle, if you have a good memory, you know in principle which cards your opponent has, which cards you have, and which cards are already played. So in principle, Schnapsen moves from this quadrant after the first phase into this one, the top one, because then you have full information. And we start now with the perfect information deterministic games, and we'll explore the other two, these two as well. Sorry, this one on this side and this one later in the lecture today. So the simple game up is usually represented as follows. You have a min player and a max player, and max starts, but in some of the examples can also in the working groups it can also be explicitly stated that min starts, but let's suppose max starts. And we have in this standard simple setup of the game, we alternate. So it's always max starting, then min, and then max and min again. Again, in a real game situation, this might be a bit more complex. So if you think Schnapsen, it's always the person who wins the trick who is allowed to continue. You would have to model that in a different way. So we start with a very simple game where max and min always alternate. And the goal of max is to achieve some kind of utility score for the game that is as high as possible, and of min as low as possible. Yeah, and that can in a simple game be just win gets a +1, lose gets -1, and a draw would be 0 if we look at Tic-Tac-Toe. But we see that there can be also more complex values given. So you start out with an initial game situation like the empty or the standard configuration of the chessboard, or in Tic-Tac-Toe with an empty board. That's again the standard initial state of your state-based problem. Then you have a number of successive functions, which are the actions that the players can take. And again, you have a terminal test, namely, is one of the players in a winning position, or have we run out of moves? That's also a possible choice. And then the important thing in the first stage is that if we have a complete information game and it's deterministic and the search space is not too big, then we can just play out all the possibilities. So with the Tic-Tac-Toe, we're going to see that you have not that many options. So it's a 3x3 matrix where you can put a cross as one player. So in principle, you have a maximal search length of 9 because you have 9 fields where you can put a number, a circle or a cross. And you have 9 choices per layer. So that's quite a search space, but it's finite and it's easy to calculate through the entire search space. But we will see later that either this becomes impossible or it will simply be too big. But for the moment, let's assume we can play out the full game, and at the end we can evaluate what the result of the game is. So in Tic-Tac-Toe, for example, does the circle win or the cross win? Or in other words, does max win or does min win? And then we have a search tree that max explores. So the goal is I'm the max player. I want to maximize my possible score. And how can I now evaluate this state space representation of the game in order to define a strategy for what I have to play in the next move? And this would be an example for a partial game tree for Tic-Tac-Toe. You start out, as I said, with the empty board, and then Max starts and puts his crosses. Max starts from here, and he puts his crosses in the board. So his actions transform the states into one of those possible 9 new states. Now it's the min turn. And min has now, of course, 8 possible actions that she can take, namely putting the round in any of the remaining 8 fields. So you have 9 by 8 by 7 is the size of your tree, until you end up in one of the situations at the end, the leaves of the tree, where you have either 3 circles in a row, or 3 X's in a row, or diagonally, or none of the 2. And if there are 3 circles in the row, max loses, so min wins, and it gets the value -1. If we have the crosses in one diagonal, or in a row, or in a column, max wins. So this would be the utility value of a final state of one of the leaf states. Could be either a draw, a win, or a loss for max. Yeah. And now the question is, can we develop a strategy for max to decide which of those will get me to a maximal value? There is an algorithm for that, which is called the minimax algorithm, and that's what I'm going to show you in a minute. Of course, the same what we've just seen for the tic-tac-toe can be done for min-max, and now for the real min-max. And we're looking for now at the phase 2, as I said. In the first phase, we're still taking back cards from the pile, and we have the uncertainty that we do not know what the adversary has in its card deck. But in the second phase, all the cards are gone from the pile, and everything is known. So it's a perfect information game, and what you basically have is one player who wants to maximize his success, one player who wants to maximize her success or minimize the other person's success, and then one starts to play, let's say Max starts to play, plays an ace, and then it's the choice of Min to play one of her cards, and basically there are some rules, as you know. In the second part of the game, you have to play the right color, so you have to follow the color of the opponent. So the search tree is much smaller than the 5 times with the 5 faculty that we would otherwise have, because if Max plays the ace, then Min has to play the 10 of clubs here. Yeah. So that's why this search tree that we get is relatively small on this level. But then on the other hand, we can branch on in the next round of the game because now Max has the choice of these 4 cards. Yeah, so it's exactly the same idea that we had for tic-tac-toe. And player who plays against your strategy, and it's always the intention for this player to maximize the utility value and for the other one to minimize it. And then the question is, what is the utility value? And this can be measured, for example, in this case, by winning or losing again. So 0 or 1 would be a draw. It also exists. So 1 would be winning for Max, -1 would be winning for Min, or a draw. Beware that this diagram shows the transitions and not the states. So the state would be after playing the card ace, would be the card deck of all those 9 remaining cards. So then the question is, do we have an algorithm that gives us an optimal strategy for each of the players? And the assumption is that both players play optimally according to the strategy. And then the algorithm is basically very, very simple, namely this idea that you calculate a minimax value for a node in the following way. If the node is a terminal, you just get the utility value. And if it's not, then you make the decision that if Max is if the node is a Max, so if it's Max turn to play the next move, you just maximize over the possible values that you can get from your opponent playing. So you maximize all the possible values that you could get after your opponent has made his or her move. And for Min, it's the other way around. So you just say that the minimax value for a node, if the node is a Min node, so Min is playing, then you just take the minimum value of the successor states. It's a very simple algorithm. It looks a bit difficult, but suppose we have this kind of game tree. So we start here with some situation, and we have 3 leaf states where in 2 of the states there's a draw, in 1 of the states Max wins. So now the question is, what is the maximum value that you can reach here? I have to see. And the algorithm is basically a recursive algorithm where you start with the leaves and then calculate the value for the root by some kind of backtracking. So basically the idea is the following. So if this player, I have to cheat a little bit, yeah. So if this player if the player in this situation can make a move and it's a max player, what is the best value for max that it can achieve for this node? One. It's a very simple question, because here max can make the choice between two values, and it will obviously always choose the highest of the two. Here, it can only choose one value, value 0. So I can now propagate the values from the leaves that I have here to the next level of choice of the max player if he comes to this situation of the game. And that basically is what I just said. So if max chooses optimally, then he will choose the 1. Now we know that in the step before, it's a min step. So min can now choose what value to take, what kind of state to take. So what is the maximum, the minimal value, the smallest value that min can get from this node? A 0, obviously. What is from this one? It's a 1, obviously. From this one, it's a 0, obviously. And from this one, it's a 1. Yeah? So you just backpropagate the values from the lower levels of the game to the higher level. So this one gets the 0 from here, this one from 1 from here, the 1 from here, and the 0 from here. And now it's one level back track. What is the maximum value that you can get here? It's a 1. What you get here is a 1. And what you get here is a 1. Okay, so all these nodes now get the maximum value of 1. And now min has to choose when she starts. So this is an example, where min starts. When min starts, she has to choose one of the states for which max will always find a winning solution. Yeah. So in this game, according to these choices that the players have, max will always win. Yeah? So, because whatever choice min makes here, in any of those states, max has a strategy to get to a winning state. If min chooses this one, then max will choose this one, then min has to choose this one, and max will choose this one, and it wins. He wins the game. Yeah? If min chooses this one, then max chooses this one, min has to choose this one, and max chooses this one again. And in the last possibility, if min chooses this one, then max will choose this one, min will choose this one, have to choose, and max will choose this one again. So in each of the three states that you can play as player max, you will have a strategy to go to one of the one value, independent of what min does. And that's the algorithm of min-max that you will implement in some more complex form. And now my question is, do we have any British people or... Huh? No, this is not baseball. That base is not baseball. Do we have any Australian, Pakistani people? No? Really not. Indian? Huh? South Africa, okay. So I guess if we have then we have only two people in the room who know and understand a little bit of the rules of cricket, because cricket is a very interesting game. It has games that take 5 days. Yes, and it's one of the few games that you can listen to on the radio without listening to much. The reason why I bring this up is that cricket has an incredibly complicated way of describing how you win. So I showed you the example of if you win the game, you get a value 1, or a value 0, or a value -1. But in cricket, you can win in many different ways. So you can win by an innings, by wickets, by runs, and all those can be combined. So it's the only thing I want to say here actually is that not all the games have very simple utility values, and surely not winning or not winning. And if you look at Schnapsen, we have even two different ways of doing that. We can measure per game, so how many points do I have at the end of the game, and I need more than 66 to win. So one utility value at the end of the game could be I win. One utility value could be I win with 72 points. And one utility value that I could have is I've won 7 games, because that is the, if you play more games, you need, a tournament in Schnapsen is 7 games. You need to win 7 games, and then you win the whole thing. So even for Schnapsen, you have 3 different ways of defining utility values. And so basically we extend this now, this idea of having linearly ordered utility values, so natural numbers. And the idea is that you can apply exactly the same algorithm for calculating the best strategy for max, even if you have now these more complicated values. So what would minimax do in this situation? So this is a choice that min has. How would the algorithm work? Does anybody see what the max value is? What is the best strategy? How many points can max make in the ideal case? No, not in the ideal case, whenever he plays optimally. 3, I hear more often. Why 3? Yeah, so min will always choose the smallest one. So this value will be a 3. Yeah, this one will be a 2, and this one will also be a 2. So we do a kind of back propagation where we say we have in the algorithm the leaf values are those. The minimum values that are chosen from the leaves are then handed back to the nodes one level higher, and then obviously max has a choice here, so he or she will choose the highest value. So the min-max decision of the worst case outcome for max is a 3. And now the only thing you have to follow is which of the nodes gives me this maximal value, and that is now the decision that max has to play in the game in order to achieve the best result. So you start with the leaves, you back propagate the values to the nodes higher in the tree, and then the strategy of max, or the starting player, is determined by which of the nodes gives you the highest utility value, and that is this one in this case. So he or she needs to play action number 1. So this is the algorithm in pseudocode, fully written up. We have a function that says minimax decision for a state returns an action, and basically you calculate the value by this function max value of the state, and you get a value back, and then you have to choose the action according to this maximal value. And then all we need to do is to implement this max value function, and that's done here. So it gets a state as an input, and it returns the utility value as we've just seen. If it's a terminal state, a leaf node, you stop, and you just return the utility value. That's what we did with the numbers 7, 8, and so forth. Then you set your value to -infinity, and you take the maximum of the ones that you have seen beneath. And the ones that you've seen beneath have to be calculated, of course, with the maximum strategy of min. So you ask, what is the maximum strategy of min applied to all of the leaf nodes, and then you take the maximum out of it. That's exactly the algorithm we've just sort of shown on the tree. And then we just have to define min value for the leaf, for the children nodes, and that's the same thing, but the other way around. So we instantiate the v value to be infinite, and then you take the minimum out of all the children underneath, and their maximum value that max can calculate. And that gives you this alternating behavior that you have max starting, and it maximizes overall the minimum states underneath. And this is min playing, and it takes the minimum values out of all the maximum values for the specific state. And I guess you haven't heard, and maybe you will not hear this notion officially, but this is a recursive algorithm because it takes some other function that in the end can call itself. So in a way, you always, by alternating, you calculate a value that solves a smaller problem, namely the subtree, with exactly the same procedure. Or, not in this case, not exactly the same procedure, but it calls exactly the same procedure in the next round. Yeah? So you don't have to tell it when to stop, it just calls itself after some row, and that is very important that you have a stopping condition, because otherwise this recursion would go on forever. So you need to have this condition that says, if something is a terminal test, then you stop your algorithm, and then you calculate all the values back. Yeah? That's something you should practice in just filling in values. Take the tree that I've just shown you before, and really try to be the algorithm, write on a piece of paper what exactly this algorithm does, because this is a very important algorithm to understand. It's really not difficult. So I would really recommend you to take your state space, the gains that we've seen before, and what you want to do is to calculate the max value of the top node. And what does it mean? It means that you have to call the max value function on this top node. And what does it mean? It's not a terminal test because we are at the root at the top of the node. So what was we don't know the value of it. I think this was kind of the shape of the tree on the slide before. You start with this node number 1. You want to calculate the max value of state number 1, and you do that. It's not a terminal test, so you look at all the successors, so that would be 2, 3, and 4, and now you have to calculate the max value, all the min values for all the successor states. So now what we have to do is to calculate min value for 2, and for 3, and for 4. Yeah? And these are now defined down here. So calculate the 2 value. It's not a leaf node. So we have to go through all the successors of 2. So these are these 3, 5, 6, 7. Now, and we have to now apply the max value on this node. But the max value for 5 in the tree that we've seen before was now a number, because this is a leaf node. Let me show you the tree again, because I remember it. You might not. So this is now where we are. This is node number 5. Yeah? And node number 5 has a value, has a utility value. So we can now calculate this to be 3. We can calculate the value for 6 to be 12, and for 7 to be 8. So now remember that in the algorithm, we're now down here, and this gives us the max values for all these successors. And the max value, we take the smallest of them, the min value, and this is then returned to this one. Yeah? It's exactly what we did before on the piece of paper, but if you plug in the values in the algorithm, it helps you to understand this. And it's important that we use the utility, some kind of value given to the possible states. So then there is some theoretical result that has been proven where we don't want to spend too much time on here. This was now under the assumption that your opponent plays optimally. And if he or she plays optimally, then this minimax algorithm will find the best possible strategy that you can find. So what has been shown is that even if your opponent doesn't play optimal, your strategy will always be optimal, will still be the best one you can find. So by playing badly according to the strategy, your opponent will also only make his or her situation worse. She can never improve on this algorithm. So basically what this algorithm does is maximizing the worst case outcome for max. Okay, so these are now the properties of this algorithm. It's complete, it always finds the best strategy. It is rather bad in terms of time, it's exponential. It's okay in terms of space, and it finds the optimal solution. So far, so good. But still, we have this problem to deal with, that it takes a long time. And playing against a game computer that takes 3,000 years to come back with the first move isn't really very nice. So we need to deal with time complexity and space complexity. First, I want to let you know that this is the first part of the milestone that you have to work on for 22nd of November. And basically what you're asked is, based on the game engine that you've played around with the last week, to now implement the first intelligent game engine that plays in the second phase of Schnapsen. So when we have perfect information Schnapsen, then your algorithm should work and always find the best and the optimal strategy. It's ideally suited for min-max because we have a perfect information game and the search space is relatively small. So it's in principle you have 10 different cards. So I have 5 cards, my opponent has 5 cards. So we have a maximum depth of 10, and the amount of the number of cards reduces. So we have 10 by 9 by 8 and so forth different cards. So that makes the search space relatively small, and that means that you can all implement that. And we've given you some code. There is some skeleton machine that you can then extend and write the rules according to the algorithm that you've seen here in the pseudocode. So that's the first part of this exercise. The second one is to do this more efficiently, and I will talk about the more efficient algorithm in a second. But I want to be really, really clear about the fact that this is a bit more advanced programming than what you're learning to program at the moment in Introduction to Python. So you will not be judged if you fail. So I want you to see you try. So what you have to do is to submit a worksheet in which you, if you fail to program the bot, but even if you manage to program the bot, just keep a very short log of what you did, what you tried, how you tried to make things work. I trust that in principle, you should all be able to do this. But if you don't panic. Just write down the things that you've tried, and that will be good enough. Because this is a pure pass-fail exercise. And if you've tried hard, you will pass and you will get the points. Yeah? It's just the intention of this exercise is to get you going, that you understand also the algorithmic principles here, and that you have something which we will then work on later in the period 6 course. So you've started with the worksheet, you run with the experiment with the existing bots, and now the next task is implement the Minimax algorithm. Okay, so we've now seen this Minimax algorithm at work. Now the question is, does this work for chess or for Schnapsen 2? I just said yes, for Schnapsen 2 it works, because the search tree becomes is reduced because we have the decreasing number of cards. But for chess, think about it. We have, let's say, 15 moves for both of the players on average. So you start out with 15 possible states or more. Then your opponent has 15. So even after one level, we have about 15 to the power of 2. And very, very easily, very quickly, the search space is so huge that you can never calculate the results anymore. There is another problem here. Does anybody see another problem? For chess, there is no uncertainty. You see all the things, you know everything. But the problem is that chess could have an infinite game. In principle, you can just move back and forth and back and forth and back and forth again. So the tree wouldn't just be incredibly wide, it would even be incredibly depth. If you might not even be able to find utility values in the first place. But even if you have the whole game, and it's finite, even then it's very difficult to determine the value of the end nodes. So that's a big problem. Yeah, so they're for a chess, just to argue back from all the games that you won or lost is far too complicated for this algorithm. It will never scale. So what you have to do is to tame the beast. You have to make the search space smaller. And basically what you do is you introduce some kind of uncertainty or imperfect information. And the idea is that we now turn from the assignment of the utility value to the end nodes to some estimation of the quality of the nodes. So again, what we did in the first lecture is we moved from uninformed search to informed search. We use heuristics to tell us whether a certain state is good or not. So basically what you do in chess, you say, okay, I can look ahead 5 steps or 20 steps or whatever, and then I stop. And even if I haven't found a state where I win or lose, what I can still say is that this state is better than another. And I use heuristics for doing that. So basically what you do in these situations is that you have a fixed step limited search. And then the time it depends on how fast you want to play and how long you want to look into the future, how much time you want to take for that in your game engine, and then you have to cut off. And then at the cutoff, you have many states in which you are uncertain about what the result is. And here you have to make the estimation. And for that, you use heuristics. The heuristics we talked about yesterday. And we can now use them for minimax as well. So the idea is that instead of using the utility state here, we use now some heuristic value. So the utility was based on the result of the game. So you win by 1 innings and 3 wickets in cricket, or player X gets 33 points, player I 69, or you win by 3 points versus 1, and so forth. Whereas in a heuristic value, you say about intermediate states of your game, which one is better, which one is more likely to win a game. So in chess, you would, for example, say if you have 2 pawns and a bishop, then this is stronger than a castle. This is a sort of a rule of thumb that a chess player knows about. Or in our game, you could say that playing the trump as is better than the random jack. That's disputable whether that's a good technique, a good heuristics, but that could be a strategy. Always play the highest card, and so forth. We've seen those kind of strategies and those kind of heuristics before for Schnapsen Light. And we have to find the right heuristic for these kind of games. And then basically what happens is exactly the same as we did before, but now we decide at a certain cutoff, at depth 4 in this case, that we stop our search. And then all these things underneath, they are just ignored. They don't count anymore. And then we make an estimation at this level of the tree where we stop the search, how good my states are. And then I apply the same algorithm. So 2 or 3 would give me 3. If I have a max choice, so here it's max turn to play. Here I would take the 9, the 7, and so forth. So here we have exactly the same minimax algorithm anymore, but now the only difference is that the values don't come from a result of a game anymore, but they come from the estimation of the quality of a state. And maybe before we have a quick break, it's quite interesting that in this case you you introduce some information in order to some information loss in order to increase performance. So we say all the tree information that is underneath the cutoff point is just forgotten. And in that sense, you create imperfect information. But still, it was very early in the AI days shown that this choice makes a lot of sense, that you have to sometimes sacrifice perfect information for efficiency and for performance. And we will look into something sort of the other side later in the lecture today. Because when you deal with the phase 1 of the game, we have to do something else. But in the phase 2 of the game, when we have in principle, we could apply a minimax. In this specific case, Schnapsen, it will work, but if you use it for Go or for chess, it doesn't work anymore. And you need this cutoff, and you need to throw away information for the purpose of more performance. And that is, I think, a good moment to stop. And we come back at 12, please. Let's have a short break. Let's start at 12 and deal that.